Let's solve example 3. We want to use the Maclaurin series for e to the x to find the Maclaurin series for this related function, which is e to the x minus 1 divided by x, and we want to express our answer in summation notation. So let's start by writing our function g of x. We have g of x equals e to the x minus 1 divided by x. We're going to use the Maclaurin series for e to the x, so let's write that down. The Maclaurin series for e to the x is the sum from 0 to infinity of x to the n divided by n factorial. For this problem, instead of keeping the summation notation, it will be helpful to expand out the first several terms before we substitute into our expression. So if we expand out the Maclaurin series for e to the x, we have 1 plus x squared divided by 2 factorial plus x cubed divided by 3 factorial, and that should be sufficient. So we're going to replace e to the x with the first several expanded out terms so we can see a pattern emerge. So e to the x we'll replace with 1 plus x squared divided by 2 factorial plus x cubed divided by 3 factorial. And we're subtracting 1 and then dividing by x. Since we subtract 1, this initial 1 here just cancels with the minus 1. And then what we're left with in the numerator is the expression x plus x squared divided by 2 factorial plus x cubed divided by 3 factorial, etc. And notice here that there's an x in every single term. So we can cancel an x in every term of the numerator with this x in the denominator. We actually have infinitely many terms here in the numerator. Each one of them is a multiple of x. So we're just going to decrease the power of x by 1 for each of these terms, and that will cancel out with the x in the denominator. So this simplifies as 1 plus x divided by 2 factorial plus x squared divided by 3 factorial. The next term would be x cubed divided by 4 factorial, etc., etc. We're simply canceling one power of x from each fraction in the numerator, and that cancels with the x in the denominator. Now we want to write this using sigma notation. What's the pattern that we see here? Well, it looks like the difference between this and the original function, the original Maclaurin series for e to the x, is that instead of starting with 0 factorial for the first term, we start with 1 factorial. So notice that under the x, instead of having a 1 factorial, we now have a 2 factorial. So one way that we could express this using summation notation is to write the sum from 0 to infinity of x to the n divided by n plus 1 quantity factorial. Try expanding out the first several terms of this Maclaurin series, and you'll see it matches with exactly this pattern that we're seeing here. So here is the Maclaurin series for the function e to the x minus 1 over x. This would be long and complicated to develop by hand using the table of derivatives and finding a pattern, but leveraging our knowledge of the Maclaurin series for e to the x, we can solve this fairly easily, and we get the answer much faster than developing the entire Maclaurin series from scratch. Example 4 is a similar example. In example 4, we have the function sine of x minus x divided by x squared. We will replace the sine of x with the first several terms of the Maclaurin series expansion. We will simplify, and then we'll notice a pattern and write the answer in summation notation. So for example 4, our function is sine of x minus x divided by x squared. We're going to use the Maclaurin series for sine. So let's write that out. The Maclaurin series for sine is the sum and goes from 0 to infinity, negative 1 to the n times x to the 2n plus 1 divided by 2n plus 1 factorial. It's important to know both the summation form, the sigma notation, and we also want to know the first several terms expanded out. Expanding out the sigma notation, we have x minus x cubed divided by 3 factorial plus x to the 5th divided by 5 factorial minus x to the 7 divided by 7 factorial, etc. We will take the sine of x in this fraction, replace it with the series expansion for sine, we'll simplify, and then we'll write down the final answer in sigma notation. So this fraction, I just simply replace sine of x with these first several terms of the expansion. X minus x cubed divided by 3 factorial plus x to the 5th divided by 5 factorial, etc., etc., minus x, all of this divided by x squared. Once again, we have some cancellations in the numerator. This plus x cancels with the minus x, and then we're left with all of these terms. There's infinitely many terms still, but all of these terms have a factor of x squared. So we could cancel out an x squared from this first term, and we'd just be left with x, We could cancel out x squared from this term, we'd be left with x cubed. Cancel out x squared from this term, and we'd be left with x to the 5th. So let's do that in the next step. We cancel out an x squared in the numerator of each of these fractions up here, and that will cancel with the x squared overall in the denominator. We have minus x to the 1st divided by 3 factorial, plus x to the 5th divided by 5 factorial. No, x cubed. The 5 cancels with the 2 here, so we get x cubed. So x cubed divided by 5 factorial, minus x to the 5th divided by 7 factorial, etc. There are many different ways that we could express this series in sigma notation. I encourage you right now to pause the video and try to write down a sigma notation expression that matches this expansion here. I'm going to write one down. It might be different from yours, but we can always check by just expanding out the first several terms of the sigma notation. So go ahead and pause the video. See if you can write out the sigma notation form for this. Here's the expression that I get. I'm going to write this as the sum from 1 to infinity, negative 1 to the n. This will give me an initial negative term. Negative 1 to the 1st gives me negative. I want negative, positive, negative, positive. So I get an initial negative term. That's good. Then I want x to the odd power. So I'm going to write x to the 2n minus 1. 2n minus 1, if I begin with n equals 1, then I'll have 2 times 1 minus 1. That gives me the initial power of 1. When n equals 2, that would be the second term. When n equals 2, I have 2 times 2, 4 minus 1, x cubed. So the powers on x are working out what I want them to be. Now for the factorials in the denominator, I can use 2n plus 1. So I divide here by 2n plus 1 factorial. When n equals 1, we have 2 times 1 plus 1, 3 factorial. When n equals 2, for the second term, we have 2 times 2 plus 1, 5 factorial. So this sigma notation is describing the pattern that we see here. So this sigma notation is describing the pattern that we want from this step here. Once again, there are equivalent forms of the sigma notation here. So your sigma notation might look a little bit different. Maybe you index starting at 0, but as long as you're getting the same terms, it's a valid answer. So here is the Maclaurin series for sine of x minus x divided by x squared. Once again, we would not want to do this by hand by making a table of derivatives. That would be quite complex. But using our knowledge of the Maclaurin series for sine, we can find the Maclaurin series for this related function. Take a look at example 5. We want to find the Maclaurin series for the function 1 over 1 plus x squared. I'm going to show you two different ways to do this. We could develop this from scratch if we wanted to by making the table of derivatives. But I'm going to show you how to use the Maclaurin series for 1 over 1 minus x, and then also the Maclaurin series for arctangent to find the Maclaurin series for this related function. We're going to see here that we get the same answer, regardless of which method we choose. We're dealing with the function f of x equals 1 over 1 plus x squared. And for part A, we want to use the Maclaurin series for 1 divided by 1 minus x. Let's go ahead and write that out. That's the sum from 0 to infinity of x to the n. And we can write out the first several terms if we want, but I think this is sufficient for our purposes here. In order to use this Maclaurin series, we want to take our original function and somehow rewrite it so that it looks like this form. So notice we have some differences here. I have an x squared instead of just x, and then I'm adding instead of subtracting in the denominator. So I want to do some algebraic manipulations here to make this look like the form of 1 over 1 minus x. I'm going to start by writing the function as just 1 over 1 minus negative x squared. So I'm getting closer to the form. I have 1 minus something, and my form for the original Maclaurin series is 1 over 1 minus x. Instead of having 1 over 1 minus x, I have 1 over 1 minus x squared. But at this point, I can just take my original Maclaurin series here and replace the x with negative x squared. And then in the summation notation, I just replace this x with negative x squared. So I can simply write this as the sum, where n goes from 0 to infinity, and instead of writing x to the n, I'm replacing the x with negative x squared. So this turns into minus x squared. We can take one step to simplify here. I'll write this as the sum from 0 to infinity. If I have negative, I can think of this as negative 1, so I can take out a negative 1 to the n here. So negative 1 to the n, that gives me my flip-flop of plus minus, and then I'm left with x squared raised to the n. Using rules of exponents, x squared raised to the n is the same as x to the 2n. Here is the Maclaurin series for the function 1 divided by 1 plus x squared. And we develop this by using the associated function 1 over 1 minus x. Let's develop the same Maclaurin series, but let's do it a different method. We're going to use the Maclaurin series for arctangent of x. Arctangent of x, looking at the front of the handout, the Maclaurin series for arctangent of x is the sum, where n ranges from 0 to infinity, of negative 1 to the n times x to the 2n plus 1 divided by 2n plus 1. Our goal is to use this Maclaurin series somehow to find the Maclaurin series for the related function 1 divided by 1 plus x squared. But how are these functions related? How is 1 divided by 1 plus x squared related to arctangent of x? Do we know a relationship here? I think we do. The derivative of arctangent is 1 divided by 1 plus x squared. So I can write 1 divided by 1 plus x squared as the derivative of arctangent of x. And now I know the Maclaurin series for arctangent of x. So I'm just going to take the derivative of this series. And when I take the derivative of this series, I'll have the Maclaurin series for 1 divided by 1 plus x squared. Here we go. Take the derivative of the series, the sum from 0 to infinity of negative 1 to the n, x to the 2n plus 1 divided by 2n plus 1. This looks really kind of intimidating. We have the derivative and the summation notation and the fractions, and there's a lot going on here. But it's not as bad as it looks. We're taking the derivative of a sum. So we're just adding up a whole bunch of stuff here and taking the derivative. And the negative 1 to the n, the 2n plus 1, these are just constants, so we don't have to worry about those. We've seen a similar sort of a problem where we took the derivative of summation notation and we said that we can just interchange the derivative and the summation. We can just flip-flop. The derivative of a sum is the sum of derivatives. So we could just write this as the sum from 0 to infinity of the derivative of whatever's left inside, negative 1 to the n times x to the 2n plus 1 divided by 2n plus 1. And negative 1 to the n and 2n plus 1, those are constants with respect to x. And since they're constants, they can just hop out in front of the derivative. So we can write this as the summation from 0 to infinity. We bring these expressions out in front of the derivative. Negative 1 to the n divided by 2n plus 1. And we're left with the derivative of whatever's left. And whatever's left is x raised to the 2n plus 1 power. So we have the derivative of x to the 2n plus 1. And this is simply power rule. We're taking the derivative of x to a constant power. We take the power, bring it out front, and reduce the power by 1. We've got the summation from n equals 0 to infinity, negative 1 to the n divided by 2n plus 1. Just copy those down. And now take the derivative of x raised to the 2n plus 1. We bring 2n plus 1 out front, times x to the 2n plus 1 minus 1, which leaves us with just 2n. And look at this. 2n plus 1 cancels. And we have the sum from 0 to infinity of negative 1 to the n, x to the 2n power. We got this by taking the derivative of the arctangent function representing arctangent with its Maclaurin series. The derivative of arctangent is the function 1 divided by 1 plus x squared. So the Maclaurin series for 1 divided by 1 plus x squared is this expression here. And take a look at this. It's the same expression as what we got from part A. We can get that Maclaurin series in two different ways. I think that's a really cool example, don't you think so? I hope you enjoyed that as much as I do.